Good morning, everybody. And in this class, we shall discuss about the theory of semiconductors. We shall discuss about the semiconductor lattices, then the transport phenomenon in semiconductors, and thereby the conductivity and mobility of semiconductors. As you know, there are some semiconducting materials available in the periodic table, towards the right side of the periodic table. And we have germanium, silicon, some compounds like gallium arsenide, and some kind of crystalline graphite, etc., as semiconductors. For instance, if you look at the germanium and silicon elements, so these are tetravalent materials. They have 4 electrons in the valence band. Now, a bulk material forms by forming covalent bonds between one atom and another atom. So look at this diagram. You have a tetravalent material with 4 valence electrons in the outermost valence state. Now, so this silicon atom, for instance, forms covalent bonds with adjacent atoms, silicon atoms, by sharing one electron each from the adjacent atoms. So the orbit is then complete, and you have a covalent bond formed between adjacent silicon atoms. And this structure repeats, and you have the bulk material available. And the strength of the bulk naturally depends on the strength of the covalent bond. This is a 2-dimensional picture. In fact, this atom forms a covalent bond with its adjacent atoms, and so on. The structure repeats. And here the structure is a 2-dimensional structure. So in actuality, the structure is a tetrahedron. So this atom forms a covalent bond with this atom, this one, and this one. So it is a tetrahedron, which is a 3-dimensional structure. And with similar tetrahedrons repeated, you have a 3-dimensional bulk. So that's what is the that's how the lattice structure of semiconductors like germanium and silicon is. Now, if you look at the energy band diagram of the electrons, so that are present in the semiconductors, so you will find that there is a conduction band, a valence band, and a forbidden band. So let us look at it more closely. When now we are considering three-dimensional space with atoms distributed throughout the space. Now, what is the behavior of a charged particle in that kind of three-dimensional space? Is it free to move about, or does it have some field or potential? what is the situation? So let us look at it in 2 dimensions at least. So wherever you have the nuclei, atom nuclei, naturally the electron gets attracted by the nucleus if there is a net positive charge on the nucleus. That means the number of electrons and the number of uh, uh, protons in the nucleus are not matching. Say when an electron approaches, the potential goes down like this, and as the electron goes out and goes close to the next nucleus, the potential goes down, and so on. If this is the end of the material, this is material, and if this is the end of the material, naturally the potential would be like this. So if a particle is moving in this field, it is not a no field situation. There is a field distribution of this type, actually the potential distribution of this type, and potential gives rise to a field. Okay, so there is a potential of this type as an electron passes by this lattice. Now an electron is a charged particle with some mass, and this is the kind of potential distribution. Now what is its behavior? If you give some velocity to it, or if you keep a stable electron here, under the influence of this potential, the electron moves in some direction, subjected to the force. Now if you analyze this problem from the wave equation and analyze this problem, so it is found that the electrons possess certain energy levels. So if the electron is a valence electron, it possesses certain energy level. This is energy. So it possesses certain energy level. And if the electron has some thermal energy, it is in the conduction band, it possesses this energy level. It can never possess this energy level. I repeat, when an electron is subjected to this kind of varying field, and you determine or you analyze this problem mathematically and see what kind of energies the electron possess, then we find that the electrons possess some discrete energy levels. So they cannot possess these energy levels. Why? Because of this kind of periodic field. When a particle is subjected to periodic field, the particle possesses discrete energy levels, not all kinds of energy levels. So so when the electron is in the innermost orbits, it possesses some lower energy levels than these. Now if you look at the outermost valence electrons, the outermost valence electrons possess certain energy levels. So EV1 to say EV2, it may have, a particular electron may have any energy level in between. Okay, and when there is some thermal energy applied on this electron, or some other potential energy by means of external field applied to this electron, it may possess some other energy. But please note that that energy cannot be between this valence band and this conduction band. So that energy will be between EC1 and EC2. So this kind of a strange phenomenon is occurring because of this kind of potential energy field. Why should they possess energy? So they are in some field. They are in field. When a charged particle is in a field, it has some energy. It can do work for you. So an iron body in a magnetic field can do work for you. Okay, it possesses energy. I'm talking about that energy. The only point is, because of the periodic structure, this energy is discrete. You cannot have any energy possible. Okay, and if this is the this is what is known as the energy band structure of a material, and naturally the energy bands and their levels, the bandwidth, the band gap in between, etc., depend on the amount of positive charge that is present in these atoms, okay, and the interatomic spacings and so on. So that means from material to material these are different. Now it is possible for an electron for a valence electron which has this energy, say at this energy, to move to a different energy level if some energy is applied to it, some external force is applied to it. So if that force can be either thermal force or it can be by means of an electrical field which is provided from outside through a battery and a parallel plates. You can create some field in between. Okay, so through external energy it is possible to elevate these electrons to a different band. And when the electrons are with this energy level, then only so it is possible for them to conduct or move and constitute a current. For instance, so in this semiconductor material which forms covalent bonds perfectly, if it is a pure semiconducting material and all atoms are, say, the silicon atoms, and all electrons are within the covalent bonds perfectly, then so this one acts like an insulator. So this material acts like an insulating material, because if you apply some small field and that small field is not sufficient to for this electron, say for example for an electron to dislodge itself from the covalent bond, it is not free for moving because it is already within the covalent bond. It's not free for moving. Therefore, by the application of some small amount of field, so this electron may not get accelerated and no current flows. Okay, so this is what happens at 0 degrees Kelvins. So a semiconductor doesn't give rise to any free electron at 0 degrees Kelvins, and therefore it acts like an insulator. Well, when the temperature rises, you have thermal energy imparted to these electrons. When thermal energy is important to these electrons, so these electrons may overcome the forbidden band and the energy level may be such that it may go up to the conduction band, and once these are dislodged from the covalent bond, they are available for flow of current and conduction takes place. This means, so this electron, for instance, when applied some thermal energy, its energy level goes up, and its energy level goes up, so the potential of itself or the energy of itself is more than the potential attraction from the nucleus, and with any small external field applied, so it may move. So when a valence electron goes into the conduction band, That means when some energy is applied to it, it is available for moving under external force. So as the temperature rises, some of the electrons goes to the conduction band and they move. I will discuss further about it a little later. Now, in the case of a semiconductor, so the energy band level is like this. Between the valence band and the conduction band, the band gap, energy band gap is of the order of 1 electron volt. So, in the case of germanium, it is about 0.72 electron volts. In the case of a germanium semiconductor, the energy gap between the valence band and the conduction band is of the order of 0.72 electron volts. So, it is moderately low. That means with little thermal energy, the valence band electrons can move into conduction band and may be available for conduction. So, this is what is the case in a semiconductor, as I have already explained. If you look at a metal, between the valence band and the conduction band, the band gap is very large. It may be of the order of 6 electron volts. So, this is in the case of it is an insulator. I beg your pardon, it's an insulator. So, in the case of an insulator like diamond, between the valence band and the conduction band, the band gap is of the order of 6 electron volts. I hope you know what is meant by an electron volt. Okay. So, the energy that is possessed by an electron when it is subjected to 1 volt potential. So, this is in the case of an insulator. So, in the case of a metal, the valence band and the conduction bands overlap. For example, this is the conduction band and this is the valence band. So, they overlap. So, the valence electrons themselves are available for conduction. This is what happens in metals like copper, silver, and so on. This is a band structure of insulators, semiconductors, and metals. Under normal temperature, like 20 to 30 degrees centigrade, a free electron, an electron which is participating in the covalent bond may get out of the influence of the nucleus and it may be out of the covalent bond and it may appear as a free electron, unbounded free electron. So, this is what happens because of the thermal energy imparted. It is not necessary that all of these electrons gets dislodged. Some electrons here and there gets dislodged from the covalent bond and they are available for conduction under external influence. And the concentration of the free electrons is of the order of 1.5 into 10 to the power of 10 free electrons per cc. typically the free electron concentration. Say this is in the case of silicon as an example. So many electrons are available within 1 cubic centimeter of semiconducting material, and under external influence, so these can move and constitute a current. If you look at the bulk at room temperature, if you look at the bulk of a material, so with so many atoms within that, from some of them some of the atoms may have a dislodged electron, and as a result of which, so there will be a net positive charge on that particular atom or ion, and there is a free electron here. So similarly, other atoms also have a net positive charge and a free electron associated with it. And these electrons are randomly distributed within the body of the material. And sometimes an electron may get and jump into the lose some energy and may jump into the covalent bond and making that atom neutral. And there may be some other atom from which an electron may get dislodged, and it may act like a positive ion, and with an electron dislodged out and it contributing for a negative charge. So this kind of interaction takes place, and some electrons may jump into the valence bands or to form the covalent bonds, and some may get out of a covalent bond, and in the process, on the average number of free electrons is of this order, 1.5 into 10 to the power of 10 per cc. Okay, this is a random phenomenon. It is not necessary that always one atom dislodges a free electron and so on. Okay, but on the average, so the average is a constant, 1.5 into 10 to the power of 10 per cc. Now, in a free body, what happens to these electrons? What happens to these electrons? Because of this kind of random phenomenon occurring, they possessing some energy, and the entire field, if you look at it microscopically, so there is a potential, a regular potential distribution, and these are electrons with different energy levels possessing some velocity. So because they possess some velocity, why should they possess some velocity? It is a region of field. Field is energy per force per charge. So because of this field, it naturally keeps moving, and as the electron moves, the field changes, sign of the field may change, and it may naturally change its direction as a result and further enter into some other field, and as a result its movement gets changed, and because of this kind of phenomenon, a free electron may be moving in a random fashion in the bulk. So if you take any cross section like this, the number of the charge crossing it from left to right and right to left on the average are equal, and therefore there is no current flows across the material when no field is applied. Well, when you apply field here, how do we do it in the laboratory? You have some parallel plates, apply some potential. So it creates some net force on there is a field setup in this direction inside the material. Because of this field, the electrons get attracted towards the positive plate because of the field. So does it mean that this electron is under a constant field? The electrons are under the influence of this field, okay, the external field, as well as the internal field, which is a periodic field distribution. Then what is the behavior of the electron in this kind of field? Well, the electron is influenced by the sum field. The sum field, if it is in this direction, the electron gets attracted in this direction. In the process, if it comes close to another positively charged atom, so the field may increase. And if it is under the influence of some other positive charge on the left of it, and if that is more than the external field applied, then it may go even in the negative direction. So even in this case also, so there would be some amount of random movement, but there would be some net right side movement, and as a result there would be electronic flow in this direction towards the positive plate, and hence there would be a current in the opposite direction because electron possesses negative charge. So the positive charge direction is in this direction. So there will be some current flowing in this direction. I repeat, still the movement of the electrons is somewhat zigzag, but there would be a net right side drift. Hence there would be a current in this direction. Well, how much would be the zigzag nature of this current, etc., naturally depends on how close these atoms are to each other, and again what is the amount of positive charge there, and the atomic dimensions of the various orbits, and how much is the external potential. Okay, any questions on this? Upper limit of conduction band. Upper limit of conduction band. The upper limit of conduction band depends on the conduction material, and the energy. If you apply a large amount of external potential, okay, so it can, the energy imparted to the electron may increase, and if the energy applied to, if you are talking about the energy within a neutral atom, so the energy can be 0 at the most, like a totally free electron, no influence, the energy can be up to 0. Okay, so these are all negative energies. What I was talking about is the sign is negative. So let me go back to this diagram. If you look at this diagram, so the electron, the potential can go up to 0 potential, where the electron possesses no energy, whereas as it goes close to the nucleus, the negative energy increases. The sign is coming because of the negative sign of the electronic charge. Any other question?
Suppose the energy provided to a valence band electron is not enough to cross the forbidden energy gap, then what happens to that energy?
Well, if it is not sufficient, so it will remain neutral. I mean, there is no, it doesn't become a free electron.
What happens to that energy? Is that lost in any way?
Or that energy will be there, that's all. I mean, that energy will be there. And the field, that means energy means what? The field is applied, the field would remain there. And only thing is you cannot have any effect of that because of no electrons. But this being a random phenomenon, and the electronic energies are also random in nature. Sometimes a thermal energy on a particular electron, imparted to a particular electron, may go beyond this energy gap and it may go to the conduction band. So this happens randomly here and there with some electrons. So with certain temperature, like from 0 degrees Kelvin, say the temperature is rise to 10 degrees Kelvin, you have the number of free electrons, a very low number of free electrons, but still there would be some number of free electrons available. Why? Again, the energies are also random phenomena. An electron may have now some energy, after some time a different energy, even if it is within the valence band. So it happens like that. Any other question?
So the energy is supplied from outside. So can the inner electrons go out into the valence?
Inner electrons, no. They are unless the energy is too high. If the energy is very, very high, yes, certainly, and in inner band electrons also may go out of, may get dislodged, and they may also become free electrons. And some free electrons, they get into the valence band. So it is possible that these electrons go out of the band and go out of the bonds and inner orbits also, in which case the metal gets breakdown. Any other question? Okay. Now let us look at the transport phenomenon in a quantitative manner. Now with well, I discussed about the conduction of free electrons under an external field. Naturally, under the external field, so these free electrons still move in a zigzag fashion, but with a net drift. Okay, and the speed they possess in the opposite direction to the field, in the case of electrons, the speed they possess is proportional to the electric field. Okay, field is force per unit charge. Under field, under force, so does a massive particle possess a uniform velocity? Force is equal to m into a. Acceleration is proportional to the force, and as a result the speed or velocity increases with time. But in the case of a semiconductor, since there are obstructions here and variable field as these electrons move, so they do possess a net limiting velocity. So the velocity would be constant irrespective of the field. Okay, under constant field, here the velocity becomes constant, and the velocity is proportional to the applied field. Unlike a massive body in free space under the influence of force, so this possesses a constant speed, constant net speed, which is proportional to the field. And the proportionality constant is usually denoted by mu, so that velocity is equal to mu into the field. Okay, so mu is known as the mobility. So under the present example, mu is the mobility of an electron, because it concerns the movement, the ability to move under the influence of a field. It is known as mobility. It is the field is measured in terms of joules per coulomb, and the velocity is measured in terms of meters per second. Therefore, what are the units for mobility? So it is meter square per volt second, because the field is measured in terms of volts per unit charge. So it is meter square per volt second. It can also be expressed in terms of joules. Now, when the charged particles like electrons can possess a particular velocity v under the influence of field E, what kind of resistance or conductivity that is exhibited by the material? Okay. On what does the conductivity of a material depend? So naturally, the number of free electrons that are available in that material, if the number of free electrons is very large, the conductivity is very high. And if the mobility is very large, naturally the speed would be large. If the speed is large, under small electric field itself, a lot of electrons flow from one side to the other side, and as a result the current will increase. And it can be mathematically shown that the current intensity across a metallic or a semiconductor body, so the current intensity can be shown as NQ into V, where N is the free electron concentration, N is the free electron concentration, Q is electronic charge,